All right, here we go. So this is AP Physics lesson 8.1 and 8.2, sort of combined. All right, these notes are basically taken from sections 8.1 and 8.2 of the Halliday and Resnick AP Physics textbook, or I guess college physics textbook. And so what we're going to be learning about is what's called potential energy and conservation of mechanical energy. All right, so here's the deal. Last chapter, we spent all this time working about the work kinetic energy theorem, right, where we learned that the net work is equal to the change in kinetic energy. And I think for some of you that was frustrating because we didn't talk about potential energy at all, right? So this chapter we get to talk about potential energy. All right, so here's the deal. So potential energy, we're going to use capital letter U to stand for potential energy. And potential energy is energy that an object has stored. And then the textbook definition is that it has energy stored due to the configuration of a system of objects that exert forces on one another. Okay? And even the book itself says that this is I don't remember what word they use, but it's kind of a nebulous definition, right? I think maybe a better definition is that it's energy that an object has stored due to its position, which is good, but still not perfect and a little bit misleading in many ways, all right? So rather than trying to hammer down a real good definition of potential energy, let's not worry about it too much at this point. In a minute, we'll learn about some examples of potential energy, different types of potential energy, and I think that'll make it a little bit clearer. At this point, the operative word is stored energy, all right? That's what you need to think about when you think about potential energy, is that it's energy that an object has stored, and it's usually because of some sort of, what we're going to learn will be a conservative force. Okay, so anyway, stored energy. All right. Now, to solve the problems, we're going to be learning about what's called conservation of mechanical energy. So for this to make sense, we need to know what mechanical energy is, all right? So we're going to use the symbol E with a little subscript MEC for mechanical energy, and that is the total amount of an object's kinetic energy and its potential energy, okay? So since we're going to talk about a couple different types of potential energy, specifically gravitational potential energy and elastic potential energy, that means that our mechanical energy of an object is going to be equal to its kinetic energy plus its gravitational potential energy plus its elastic potential energy. All right. Now, please note, and this is not sort of obvious by looking at the equation, when you use this equation, you're using this equation to find the mechanical energy at one instant in time. Okay. So it would not make sense to find the kinetic energy, when you first throw the ball, and then add that to the gravitational potential energy when it's at the top of the path, okay? You have to, oops, I spelled the word one wrong. That's embarrassing. So when you find the mechanical energy, you're adding up your different forms of energy at one instant in time, okay? It's very important, all right? So let's talk about the different types of potential energy, all right? So the first type we're going to talk about is called gravitational potential energy. We're going to use the symbol UG for it. And that's potential energy that an object has stored due to its separation from some object, usually the Earth, to which it has some significant, I should have put that word in there, some significant gravitational attraction, all right? So the idea is this, so check it out, here's the Earth, right? And you've got a ball up here, right? So because the ball up here is separated from the Earth, if we release the ball, then it'll move down and it'll go faster and faster and faster, right? And gain kinetic energy, right? So one way to explain that would be to say that the ball, that gravity did work on the ball. And, as a result, it gained kinetic energy, okay? Another way to think about this would be to say that because the ball is separated from the Earth by this distance d, it has the potential to fall down that distance, right? Okay. And so instead of explaining it in terms of gravity doing work, we could say that the ball started out with stored energy because of gravity. Okay. So different ways of kind of saying the same thing. All right. So here's the deal. So last chapter we learned that when you lift an object that you're doing work, right? And weirdly, to figure out how much work you did lifting an object, we used the work kinetic energy theorem, right? All right, so what we would do is we'd say this, all right, so here's your box, it's sitting on the floor, right? And we're gonna lift it up onto this shelf up here, right? And so what we did was we said, all right, well, the kinetic energy here is 0. We're gonna lift it up onto the shelf, so the kinetic energy here is 0. So that means that our net work is 0. Well, that net work is equal to the work done by gravity plus the work done by you, right? Because those are the only two forces, you and gravity. Well, the work done by gravity would be equal to the force of gravity times the displacement, right? So this is equal to the force of gravity times the displacement, right? Which, I guess maybe I should just write it this way. So your force of gravity is just mg, but it's negative, right? And then times your displacement, right? So the work that gravity did there would be negative because the force of gravity is down, the displacement's up, right? And since your net work is 0, that means that the work that you did must be this, right? Okay? So the question is, so you did work, but the box didn't sort of gain any kinetic energy. So what we're going to do is this. Even though you haven't changed the kinetic energy, we're still going to consider you as having changed the mechanical energy, all right? So from this point forward, when you lift an object, we're going to consider this a change in the gravitational potential energy, okay? So when you lift the object, you are changing the gravitational potential energy. So even though you're not changing the kinetic energy, you are still changing the mechanical energy because you're changing the gravitational potential energy. Made that harder than I needed to. All right, so here's how we're going to calculate gravitational potential energy. I'm just going to multiply the mass of the object times the acceleration of gravity times y, okay? And in this example here, y is your vertical position, all right? So when you start a problem, you've got to pick an origin. What point do you want to be a vertical position of 0? So in this problem over here, the common sense thing to do would be to call the ground a position of 0, and then measure up from there. So just know that the potential energy, the gravitational potential energy that you get is going to depend on what point you pick to be a y of 0. So you and a friend might solve a problem, but pick different points for y equals 0 and get different potential energies. And while that will change the gravitational potential energy, it will not change, the solution to the problem, which, usually we'll be asking for velocity or for work or for whatever. Okay? All right, so that is gravitational potential energy. So we should probably do a quick example here. So let's suppose that over here in this example that we've got up here, let's suppose that the mass of our box is, I don't know, let's say that it's whatever, let's say 12 kilograms, right? Okay, and maybe we're lifting it up a displacement of 5 meters, right? So that means that our y, or vertical position, once we're done lifting the box, is going to be 5 meters, right? So then that means that our gravitational potential energy is mgy, which is 12 kilograms times 9.8 meters per second squared times 5 meters. So multiply this all out. Notice you are going to get Newton meters or joules. And in this case, you get 588 joules. Okay. So that is the deal with gravitational potential energy. All right? Cool. So anytime you lift an object, you are giving it gravitational potential energy. And if you lower it, you're taking away gravitational potential energy. Okay? All right, now, next type of potential energy is called elastic potential energy. So again, this is going to be stored energy, but this time it's being stored because of an elastic object that is either being stretched or smooshed, technically compressed, but for whatever reason I enjoy the word smooshed. All right, so usually when we talk about elastic potential energy, we're going to be talking about the elastic potential energy of a spring, okay? So we've already talked about work done by a spring, right? So we learned that the work done by a spring was 1/2 kxi squared minus 1/2 kxf squared, right? Now, so over here, when you do work to stretch or compress a spring, the work that you do is this, right? It's the opposite. So instead of initial minus final, it's final minus initial. Cool. So I think that's that. I think we already know what all of this is, right? K is your spring constant, right? And then X is the position to which the spring has been either stretched or smooshed, right? So if you've got set up like this, then you're going to call the relaxed point on the spring a position of 0, and then you just set out your number line from there. So here's a position of 1, 2, 3, -1, -2, etc., meters. Okay? So again, as with gravity, when you lift something, you're not necessarily changing the kinetic energy. Well, similarly, if I stretch the spring, from here to here, I'm not necessarily changing the kinetic energy because it might start and stop at rest. So when you lift something, the work that you're doing is going into gravitational potential energy. When you stretch or smoosh a spring, the work that you're doing goes into elastic potential energy. And so if the spring starts at rest, well, I guess it doesn't even matter. The potential energy of a spring at a given position is 1/2 kx squared. All right, so in the same way as if you drop an object, you can convert gravitational potential energy into kinetic energy. Here, if you've got a spring that is either stretched or smooshed, the stored elastic potential energy can be converted into kinetic energy, right, by letting the spring push or pull the object. All right, so those are the two types of potential energy. All right, now, because both gravity and springs have a form of energy associated with them, we're going to call them conservative forces. All right, so the technical definition of a conservative force is that it is a force in which the amount of work done by the force on an object moving between 2 points doesn't depend on the path taken, or if the work done by the force on a closed path is 0. So what that's saying is a force is conservative if, suppose I've got an object that moves from point A to point B. All right, so and then the object moves from point A to point B. So if, maybe this is one path, here's another path, here's another path. All right, so a force is conservative if the work done by that force along each of these 3 paths is equal. Okay. Alternatively, if you've got an object that starts at point A, and then it follows any closed path so that it does maybe this, or maybe it, does one of these, right? Or maybe it does whatever, this, right? So that little green object that I drew in all 3 of those cases both started and ended at the same spot. So that means that the work, so if the force is conservative, that means the work done on any of these 3 paths over here has to be 0. Okay, so that's a little abstract. So let's talk about some very specific examples. All right, so gravity is a conservative force. All right, which is why we have gravitational potential energy. All right, so we've seen this before, right? If you've got a frictionless slide with a ladder on it, and the slide is 3 meters tall and 5 meters long, then let's see. So here's the slide. Oh my gosh, it's terrible. So here's the slide. So what did we say? We said that it's 3 meters tall, 4 meters long. Oh my gosh. 3 meters tall, 5 meters long. That means this other side over here is going to be 4 meters, right? So it says on Monday, Sally has a mass of 30 kilograms. She's going to climb down the ladder and then walk to the bottom of the slide, right? So here's Sally. So if she goes down the slide, then gravity is going to do a work equal to mg times 3 meters, right? Okay. And then when she walks from the bottom, walks from there to the bottom of the slide, gravity's not doing any work, right? Now because her displacement as she walks here is perpendicular to the force of gravity, right? So the work done by gravity, if she walks from the top of the slide, down the ladder, and across, the work done by gravity would be this number here, right? mg times 3. So I guess we could actually figure it out, right? Work done by gravity would be her mass, which we said was 30 kilograms. 30 kilograms times 9.8 meters a second squared times 3 meters, right? So that gives us, what's 90, what is that, 882 joules? All right, so that's the work done by gravity there. So, and then we've seen this when last chapter we saw this. So the next day she gets up some courage and she goes down the slide. All right, and if you figure out the work done by gravity, again, you end up getting Fg times d times the cosine of theta, right? So let's see, our Fg is going to be 30 kilograms times 9.8. Our d here is the 5 meters. And then the cosine of theta is, well, if this is theta, then cosine of theta is adjacent over hypotenuse, right? So times 3 over 5. Notice the 5's cancel, and you still get 30 times 9.8 times 3. Okay? So, long story short, the work done by gravity is the same on both of these paths, okay? Which means that it's a conservative force, all right? And it turns out similarly that, I think I didn't make a slide for this, yeah. It turns out similarly that if you've got, you know, a spring, with a box on it, if you take the spring and squish it and move the box to here, you will have done some amount of work. I guess I should say the spring will have done some amount of work, since that's the conservative force here. So a spring will have done some amount of work as the box moves from point A to point B. If you, the next day, come back and do this with the box, then the spring will have done the same amount of work, okay? Because the force of a spring is a conservative force, all right? Okay, it turns out that most forces are not conservative, right? Because if you've got, So imagine a crate sitting in a warehouse. So here's a top view. Here's the crate. We're going to move it from point A over here to point B, right? So if you push it in a straight line, then your force of friction is going to be whatever your force of friction is, and this is going to be your displacement, right? Whereas if you do this, then the force of friction is the same, right? But your distance is going to be significantly bigger. So the work done by friction is going to be a lot larger, okay? And similarly, if Roy is pushing it, same idea, right? The work that he does is going to be different, okay? So most forces are not conservative, all right? So it turns out that this explanation of conservative and non-conservative forces really can help us, all right? So if you've got an isolated system where there are only conservative forces doing work, it turns out that the mechanical energy of the system will remain constant, okay? Now, please remember, this is only if only conservative forces are doing work, okay? So you might have non-conservative forces, but they can't be doing work, okay? So we'll do a simple example. Before we do, one quick, I guess, definition or equation that's going to come in handy, which is this. The work done by a conservative force is equal to the opposite of the change in conservative potential energy. In English, so if you've got, here's what this is saying. Suppose you've got a box that's going to fall. So the idea is, as this thing falls, it's going to lose gravitational potential energy, right? So here, let's just pick some easy numbers. So suppose that this thing has a mass of, say, 2 kilograms, and it's got a vertical position of 5 meters, right? So that means that my gravitational potential energy here is going to be mgh, right? So that gives you 98 joules, right? So as it falls, once it gets down to here, the gravitational potential energy is going to be 0, right? Because our y is 0. So in this example, our change in gravitational potential energy is negative 98 joules, right? Because we lost 98 joules worth of energy. Well, how much work did gravity do? Well, my force of gravity is mg, right? So that's, well, negative mg, I guess, right? So it's going to be negative 2 times 9.8, so negative 19.6 newtons. And then it's going to fall down at a displacement of 5 meters, so 19.6 times 5. You find out that the work done by gravity is positive 98 joules, all right? Okay, so the work done by a conservative force is the opposite of your change in the potential energy due to that same force, okay? Here, in this example, we lost 98 joules of gravitational potential energy, and gravity did positive 98 joules worth of work on the object to make that happen, okay? All right, now, if the object is just falling here, in this example that I've drawn, then that gravitational potential energy turns into kinetic energy, right? Okay, so probably the easiest way to do this is by doing an example. So this is sort of the classic roller coaster example. All right, so what we've got here is a roller coaster. So it tells us that it's frictionless, which means that we don't need to worry about that particular non-conservative force. Okay, and it says that Roy goes over to the top of the first hill that's 50 meters tall, so that's up here, at 10 meters a second. All right, and then it says find his velocity at the top of the first loop, which is 30 meters tall, is question A, and then B wants to know the height of the second hill. So one of the things that I find useful is that it's helpful to sort of name your points. All right, so I'm going to call this point up here, I'm going to call that point T for the top of the loop, or sorry, the top of the hill. I'm going to call this point L because it's on the loop, and I'm going to call this point H because it's the top of the hill. Okay. So as we go along the ride here, the only forces, there's no friction, so the only forces are going to be gravity, which is conservative, and normal force. And although normal force is not conservative, it's not actually doing any work, right? Because the force of gravity is perpendicular to the direction of motion at any given moment. Okay. So to solve this thing, here is what we're going to do. I'm going to first of all note that the only forces are conservative. So that means that the mechanical energy at the top of that first hill is going to equal the mechanical energy at the top of the loop. Okay? So that means that the kinetic energy at the top of the hill plus the gravitational potential energy at the top of the hill has got to equal the kinetic energy at the top of the loop plus the gravitational potential energy at the top of the loop. Okay, well, kinetic energy, so that's 1/2 m times the velocity at the top of the loop. So I did not do what I usually do, which is this. Let's take a minute and write down our givens. So at the top of the hill, we know that our velocity is 10 meters a second, and our vertical position is 50 meters. So that's described as the height of the hill, right? So what I'm doing is I'm assuming that ground level is a height of 0 in this whole problem. Okay? All right, now when we get to the loop, it tells us that it's 30 meters tall, but we don't know the velocity. And then the second hill, this is for question B, we're trying to find out how high it is, but we know that the velocity is 30 meters per second. Okay, so going back over here to my problem. So my kinetic energy at the top of that first hill is going to be 1/2 m. Well, here, let me write this out, I guess, with letters first. So this is going to be 1/2 the mass times the velocity at the top squared plus mass times g times y at the top, right? So that's going to equal 1/2 the mass times the velocity on the loop squared plus mg times y on the loop. Okay, so at this point, basically, we know all of our numbers. We're just going to solve for the velocity at the top of the loop, right? Oh, I'm lying. We don't know all of our numbers. So let's plug in the numbers we know. I guess at some point the masses are going to cancel. I'm just deciding if I want to cancel them now. I might as well since I brought it up, right? So notice all of these terms have an m in it, right? So if I divide all of this by m and I divide all of this by m, then the m's go away. Okay? So now here's my equation. 1/2 the velocity at the top of the first hill squared plus g times y at the top of the first hill. It's got to equal 1/2 the velocity on the loop squared plus g times y on the loop. Okay? So here we go. We're going to get 1/2 of 10 meters a second squared plus 9.8 times y at the top of the loop is 50 meters equals 1/2 the velocity on the loop squared plus 9.8 meters a second squared times 30 meters, right? Okay, so we've got this equation here, which the only variable here is the velocity on the loop. So algebra your way through that, and you will discover that the velocity at the top of the loop turns out to be 22 meters per second. Okay? All right. And then part B is very similar. I'm not going to do that because it's really just more algebra. The only difference is you'll know the velocity at the top of the hill, and you'll be solving for h instead. Okay? So try that on your own. Please do that. And then if you're struggling with it, come talk to me. All right? Okay, so one last final example. All right, so here we go. So now we've got Wile E. Coyote. He's got a mass of 20 kilograms, and he's going to use the slingshot to try to catch the Roadrunner. All right, so we're going to treat the slingshot as just like a single spring with a constant of 120 newtons per meter. So let's write that down. K here is 120 newtons per meter. It says assume that the spring is relaxed. Assume that a relaxed length of the sling is the same as the distance between the posts at the top. That's a really complicated way of saying assume that this point up here at the top of the slingshot is where the slingshot is relaxed. Okay. All right, it says he stands at rest at the bottom of the slingshot as shown before lifting his feet to be launched. All right, so the idea is once he lifts his feet to be launched, and this is a little bit sloppy here, but some sort of cartoon physics here. But once he lifts his feet to be launched, the only forces that are going to be acting on him are the slingshot and gravity, right? Both conservative forces, all right? So let's name our points. So there's going to be 3 points we're going to care about. So we're going to call this point I, it's our initial point. All right, we're going to call the point up here at the top, so he's going to get flung forwards, right? Funk, like this, right? So we're going to call this point R, as in release point. That's the point where he's released from the slingshot. All right, and then question 2 wants to know what's going on at his highest point, so we'll call that T for top. Okay, so to solve number 1, it says find his velocity as he's released from the slingshot. So the idea is I know that the mechanical energy initially has got to equal his mechanical energy as he's released. Okay? So, mechanical energy initially. Well, at this point, we can call this, let's call that a height of 0, right? So that means that he doesn't have any height at this point. So all of his mechanical energy initially is elastic potential energy, right? So that's going to then equal, well, as he's flung forward, he's also moving up, right? So at this release point, he's not going to have any elastic potential energy anymore because the slingshot is now relaxed, but he's going to have some gravitational potential energy at that release point, and he's going to have some kinetic energy at that release point, okay? So let's see. Elastic potential energy initially, that's 1/2 times K times xi squared, okay? That's got to equal his mass times g times his y at the release point plus 1/2 his mass times his velocity at the release point squared. All right, let's plug in our numbers. Let's see. 1/2 K is 120 newtons per meter. His x initially is the distance that this has been stretched, which is 8 meters. Don't forget to square it. That's going to equal his mass, 20 kilograms, times g, which is 9.8 meters a second squared, times his y at the release point is this 4 meters, right? Plus half of his mass, which is 20 kilograms, times the velocity at the release point squared. Okay, so that's that. So if you solve this, the velocity that you get ends up being, it's like 17.48 and then some other numbers. And obviously for SIGDIGS, I rounded it off to 17.5. When I solved number 2, though, I did not round it. I used this unrounded number, okay? So just note, I think that if you solve number 2 using just 17.5, because of rounding, this answer ends up being a little bit lower, but whatever. Okay, so there you go. So that's part A. Okay, so to do part B, let me clear up the board here. Oh shoot, I just erased something that I didn't want to erase. All right, so to do part B, we want to know how high he is at his highest point. So a couple things. So first of all, when I did this first one, number 1, the first thing, the equation that we had here was this. We had that is elastic potential energy initially equals some other stuff. So it turns out if you figure out what that number is, it's 3,840 joules. Okay? So when he gets to his highest point, so here he is, here's the little slingshot, and he's going to go, right? So when he gets to his highest point, he's going to have two types of energy. He's going to have kinetic energy, and he's going to have gravitational potential energy, right? So his kinetic energy at the top, well, all of his motion there is horizontal. So at the top, I need to figure out what his velocity is. Well, it's horizontal. So the idea is when he comes out of the slingshot, we just figured out, I do not like that drawing. Let me clear that up a little bit. Oh, much better, right? No. All right, so the idea is his velocity, we just figured out that was 17.5 meters a second, right? But that is at this angle, right? Because he's going to go straight up this way, right? So we got to figure out what this angle is. Well, look at this triangle. Let me clear it up a little bit here. Got too much clutter on my drawing here. So if you look at this triangle, 8 and 4 and horizontal, since this is half of this must be a 30, 60, 90 triangle. So this angle here has got to be 30 degrees. So the Vx is just going to be 17.5 times the cosine of 30 degrees. And again, I didn't use 17.5. I used that unrounded number. Okay, so when you find that Vx, you end up getting 15.139 meters a second. All right, so that's the horizontal velocity he has when he's launched, and one of our rules of projectiles tells us that that horizontal velocity is constant. So at the top, his velocity is 15.139 meters a second, which means that his kinetic energy corresponding with that, if you figure it out, excuse me, it turns out to be 2,292 joules. Okay? All right, well, that means that, so remember, at the beginning, this elastic potential energy, that was his mechanical energy initially, right? So his mechanical energy at the top has to be the same thing. So that means, so this is at the top, we know that our, we know that our mechanical energy has got to add up to 3,840 joules. So some of our energy is kinetic, that means the rest has to be potential energy. So subtract these two guys and you'll find out that your potential energy at the top is 1,548 joules, right? So that these all add up. Okay? And now that you know the gravitational potential energy at the top, you can find y at the top. So Ug equals mgy, which means that y is gravitational potential energy over mg. So if you take this and divide it by mg, it gives you your height, which turns out to be 7.90 meters. Okay? So there we go, conservation of mechanical energy.